April 3, 1945. Off Okinawa. Fire Controlman Second Class Thomas Hendricks watched the sea state through the optical rangefinder of Mount 52 aboard destroyer USS Laffey, calculating angles that shouldn't have mattered. The kamikaze approaching from starboard was flying so low, its propeller wash kicked spray off the wave tops, below the depression limit of his 5-inch 38 mount, theoretically untouchable by the ship's main battery. Theoretically, Chief Gunner's mate, Robert Johnson, manning the mount captain's position directly behind Hendricks, had different orders. Orders that contradicted every principle of anti-aircraft gunnery Hendricks had learned at Great Lakes Naval Training Station. Set proximity, bearing 270, elevation -2 degrees. Fire into the water ahead of the target. The logic seemed insane. Their 5-inch shells travelled at 2,800 feet per second. The kamikaze, a Mitsubishi A6M Zero modified for suicide attack, was approaching at perhaps 250 miles per hour. Firing at the water meant aiming at nothing, wasting ammunition on empty ocean while the aircraft continued its approach unmolested. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. But Chief Johnson had seen something during the Philippine Sea campaign that transformed his understanding of anti-aircraft warfare. He had watched proximity-fused shells detonate 30 feet above the water's surface, creating a wall of shrapnel that destroyed low-flying aircraft without requiring a direct hit. The shells didn't need to strike the target, they simply needed to explode near it. And if you fired into the waves ahead of a low-flying kamikaze, the proximity fuse would sense the ocean surface first, detonating the shell in the aircraft's flight path before the pilot could maneuver away. What Hendricks and thousands of other Navy gunners couldn't yet fully comprehend was that they were employing the most closely guarded secret of the Pacific War, more restricted than the Manhattan Project in some respects. The VT proximity fuse, a miniature radio transmitter and receiver packed into the nose of a 5-inch shell, spinning at 1,500 revolutions per second, withstanding forces of 20,000 Gs during launch, and calculating the distance to nearby objects by measuring reflected radio waves. A device so revolutionary that its existence was concealed from American personnel until absolutely necessary, and whose principles remained classified long after the war ended. The kamikaze doctrine had evolved from desperation into systematic tactics by spring 1945. Vice Admiral Takejiro Onishi had formalized the Special Attack Corps in October 1944, recognizing that conventional attacks by diminishing numbers of trained pilots against the American fleet's overwhelming firepower produced minimal results. But kamikaze attacks, which guaranteed the aircraft and pilot reached the target, achieved damage ratios that justified the horrific cost. Early kamikaze missions during the Philippines campaign had achieved approximately 14% hit rates, compared to less than 2% for conventional torpedo and dive bombing attacks. The mathematics were brutal but undeniable. Japanese pilots quickly learned that high-altitude approaches gave defending gunners too much time to track and engage them. Medium-altitude attacks, while faster, still provided American radar operators sufficient warning to vector combat air patrol fighters onto incoming raids. But low-altitude approaches, with aircraft skimming the wave tops at 50 feet or less, could defeat American search radar and reduce engagement times to seconds rather than minutes. The curvature of the earth and the sea return that cluttered radar scopes meant that a kamikaze, approaching at wave-top height, might not be detected until it was 5 miles from the target, giving defenders perhaps 90 seconds from detection to impact. The USS Laffey, DD 724, was a Sumner-class destroyer displacing 2,300 tons, carrying 6 5-inch 38 caliber guns in 3 twin mounts, 12 40mm anti-aircraft guns in twin mounts, and 11 20mm cannons. Her crew had been at general quarters for 4 hours on April 3rd, part of Radar Picket Station No. 1, 16 miles northwest of Okinawa, where destroyers served as early warning outposts for the invasion fleet. The assignment was effectively a death sentence. Radar picket destroyers absorbed the first waves of kamikaze attacks, sacrificing themselves to provide warning for the transports and capital ships behind them. Fire Controlman Hendricks had joined Laffey's crew at Puget Sound Navy Yard in February 1945, part of a replacement draft after the ship's original commissioning crew had rotated stateside. His training at Great Lakes had covered standard anti-aircraft procedures, optical rangefinding, fuse setting, and ballistic calculations for hitting maneuvering aircraft at altitude. Nothing in that training had mentioned shooting into the ocean. Nothing had explained that the nose of every 5-inch shell in his ready magazine contained a vacuum tube radio set that would revolutionize naval warfare. The development of the proximity fuse had begun in 1940, when British scientists approached the United States with a desperate request. German bombers were devastating British cities, and the Royal Air Force's anti-aircraft defences were proving inadequate. Traditional anti-aircraft shells used mechanical time fuses, requiring gunners to calculate exactly when the shell would reach the target's altitude, set the fuse accordingly, and hope the aircraft hadn't manoeuvred by the time the shell arrived. Hit rates rarely exceeded 5%, often much less. The British needed a shell that would explode automatically when it passed near an aircraft, eliminating the requirement for perfect fuse timing. The theoretical solution was obvious: a radio proximity fuse that would measure its distance to nearby objects and detonate when that distance fell below a preset threshold. The practical challenges were staggering. The device had to fit inside the nose of a 5-inch shell, approximately 4 inches in diameter and 6 inches long. It had to survive the shock of gun firing, which subjected components to forces exceeding 20,000 Gs, equivalent to a sudden acceleration to 15,000 miles per hour in the first millisecond. It had to function reliably after spinning at 1,500 revolutions per second for 30 seconds of flight time. It had to distinguish between the target and the ocean surface, clouds, or other objects. And it had to be mass-produced by the hundreds of thousands, cheap enough to expend one per engagement, yet reliable enough to trust with defending ships and lives. The National Defense Research Committee, established in June 1940 under Vannevar Bush's direction, assigned the Proximity Fuse Project to Section T, headed by Merle Tuve at the Carnegie Institution's Department of Terrestrial Magnetism. Tuve assembled a team of physicists and engineers who understood that every component would have to be reinvented. Standard vacuum tubes, with their delicate glass envelopes and thin filaments, would shatter instantly under gun-firing forces. Standard capacitors and resistors would disintegrate. Even the solder connections between components would fail under the acceleration. The solution required developing entirely new manufacturing techniques. Engineers designed rugged vacuum tubes with heavy filaments, supported by multiple glass beads, envelopes thick enough to survive shock, yet thin enough to remain electrically functional. They invented battery cells that could withstand 20,000 Gs without rupturing, providing electrical power for the 30 seconds of flight time. They created capacitors using ceramic materials that wouldn't crack under stress. They developed special solders and crimping techniques that would hold electrical connections together when conventional methods failed. Every component represented months or years of experimentation, testing thousands of variations until they found designs that worked reliably. The radio circuit itself was elegantly simple in principle, maddeningly complex in execution. A small oscillator, powered by the battery and built around a miniature vacuum tube, generated radio waves at frequencies around 180 MHz. These waves radiated from a small antenna in the fuse nose, reflecting off any nearby objects, ships, aircraft, even the ocean surface, and returning to a receiving antenna. When the returning signal exceeded a threshold, indicating the fuse was within 70 feet of a large object or 30 feet of a smaller one, a thyrotron tube would fire, triggering the detonator and exploding the shell's high explosive charge. The critical innovation was the thyrotron switching tube, which could reliably trigger under extreme conditions while spinning rapidly. When the received signal strength exceeded the threshold, the thyrotron would ionize and conduct current, firing a small explosive detonator that initiated the main charge. This process occurred in microseconds, fast enough to ensure detonation at the optimal distance from the target. The entire circuit, from oscillator to thyrotron to detonator, had to function flawlessly after being shot from a gun barrel at speeds exceeding 2,000 feet per second. Testing proceeded at the Naval Proving Ground in Dahlgren, Virginia, and at other facilities. Engineers fired thousands of prototype fuses from guns, analyzing failures to understand which components broke and why. They tested fuses against towed targets, measuring detonation distances and reliability. They conducted static tests, subjecting fuses to controlled shock loads on specialized machines that simulated gunfiring. Each test cycle revealed new failure modes that required redesigned components and additional testing. The development program consumed 2 years and tens of millions of dollars before producing a design reliable enough for combat use. Production began in mid-1942 at facilities across the United States. The manufacturing challenge was extraordinary. Each proximity fuse contained approximately 100 individual components, many requiring precision assembly under magnification. Workers, predominantly women recruited from civilian life and trained in techniques they couldn't fully understand due to security restrictions, assembled fuses by the thousands. The Eastman Kodak Company, Crosley Corporation, Sylvania Electric, and other contractors established production lines, eventually producing over 22 million proximity fuses before the war ended. The cost per unit, initially over $700, eventually dropped below $20 through improved manufacturing techniques and economies of scale. Security surrounding the proximity fuse was absolute. The device was classified above top secret, with special handling procedures that exceeded those for most code-breaking materials. Fuses could only be used over water, where duds would sink and be unrecoverable by the enemy. Using proximity fuses over land was strictly forbidden until late in the European War, when the Battle of the Bulge created circumstances desperate enough to justify the risk. Even then, recovery teams followed advancing infantry to collect any unexploded shells before German forces could examine them. The Japanese never captured an intact proximity fuse during the entire war, denying them any opportunity to copy or develop countermeasures. The secrecy extended to American personnel. Gunners like Fire Controlman Hendricks received proximity-fused ammunition without explanation of how it functioned. They were simply told that VT meant variable time and that these special fuses would automatically explode at the optimal distance from the target. The actual radio principles remained classified. Gunnery officers attended special briefings where they learned that proximity fuses were most effective when used in specific circumstances, including against low-flying aircraft, where setting the fuse to detonate above the water's surface would create a lethal barrier. Chief Johnson had attended one such briefing in Pearl Harbor during Laffey's workup period. The instructor, a commander from the Bureau of Ordnance, had explained the seemingly paradoxical tactic of firing into the water. When a kamikaze approached at wave-top height, standard time fuses were ineffective because the time of flight calculations assumed the target was at altitude. Setting a time fuse for surface burst required perfect range estimation and perfect timing, both impossible against a maneuvering target in combat conditions. But a proximity fuse, set for normal operation, would sense the ocean's surface first, when the shell arced downward in its trajectory. It would detonate approximately 30 feet above the water, creating a cone of shrapnel that extended several hundred feet forward along the shell's path. A low-flying aircraft entering that shrapnel pattern would be destroyed or damaged, even though the shell had never directly approached it. The mathematics were counterintuitive, but sound. A 5-inch .38 shell contained approximately 4 pounds of explosive. Upon detonation, the shell casing fragmented into approximately 15,000 individual pieces of shrapnel, ranging from small fragments to pieces weighing several ounces. These fragments radiated outward at initial velocities exceeding 4,000 feet per second. Against an aircraft traveling at 250 miles per hour, approximately 367 feet per second, the relative velocity of shrapnel was overwhelming. Even small fragments could penetrate aluminum skin, sever control cables, puncture fuel tanks, or wound the pilot. A single hit from a fragment weighing more than an ounce could destroy an engine or structural component critical to flight. The proximity fuse's detonation at 30 feet above water created a shrapnel pattern approximately 400 feet long and 200 feet wide when the shell was fired at low angles. An aircraft flying into that pattern had an extremely high probability of taking multiple hits. More importantly, firing ahead of the target, into the water in its flight path, meant the shrapnel would still be effective even if range estimation was imperfect. The aircraft was flying toward the detonation point rather than trying to outrun a shell fired directly at it. This reversed the geometry of engagement in the defender's favor. Japanese pilots had developed their low-altitude approach tactics specifically to defeat American gunnery. By the time Laffey deployed to Okinawa in April 1945, kamikaze tactics had been refined through 6 months of operations. Pilots learned to approach from the direction of the sun when possible, using glare to blind optical rangefinders. They learned to fly in coordinated groups, overwhelming defenses through sheer numbers. They learned to jink violently during the final approach, making tracking difficult for gunners following them with optical sights. And they learned that flying at 50 feet or lower made them almost impossible to hit with traditional anti-aircraft fire, as most shells would either miss entirely or detonate after passing the target. This final tactic had been devastatingly effective during the Philippines campaign. Destroyers on radar picket duty had watched helplessly as kamikazes skimmed toward them below. The depression limits of their 5-inch guns, too low for effective fire control. By the time the aircraft rose to strike, usually in the final 500 yards, gunners had only seconds to engage with automatic weapons that lacked the range and hitting power to guarantee kills. Multiple ships had been hit, and some sunk by aircraft that their main batteries could not effectively engage. The introduction of proximity fuses, combined with the counterintuitive waterburst tactic, restored effectiveness to the 5-inch batteries against low-altitude threats. The tactic had first been employed experimentally during operations off Iwo Jima in February 1945, where destroyers reported successful engagements against low-flying aircraft using fuses set to burst on water. The results were dramatic enough that fleet gunnery officers issued guidance to all ships in the Okinawa operation, officially sanctioning the waterburst technique and providing firing solutions for various engagement geometries. Fire Controlman Hendricks checked his ready ammunition status. Mount 52 carried 20 rounds of ready ammunition in the handling room directly below the gun mount, with additional shells stored in magazines deeper in the ship. Approximately 60% of his ammunition load was proximity fused, with the remainder being conventional time-fused shells for use against high-altitude targets, where proximity fuses might detonate prematurely on clouds or rain. The ammunition handlers had been trained to identify VT-fused shells by markings on the fuse nose and to load them on command from the mount captain. The kamikaze approaching from starboard was now 3 miles distant, still at wave-top height, its engine noise audible over the sound of Laffey's own machinery and the wind. Hendricks could see it intermittently through the spray, a dark speck against the grey ocean, growing larger with each second. The aircraft was a Zero, its distinctive elliptical wing planform visible even at this distance. Zerusen, modified for kamikaze use, typically carried a single 250-kilogram bomb beneath the fuselage, converting the fighter into a manned missile with 1,700 pounds of high explosive. A hit anywhere on Laffey would likely be fatal. Chief Johnson's voice crackled over the mount intercom, steady despite the circumstances. Train right, steady on 280, elevation -1, load VT common, fire on my command. Hendricks adjusted the optical sight, tracking the aircraft as it maneuvered slightly, then settling on a point in the water ahead of its flight path. The mathematics were simple once you accepted the premise. The aircraft would take approximately 30 seconds to cover the remaining distance. The 5-inch shell would reach the aim point in less than 5 seconds. Detonating above the water, it would create a shrapnel barrier that the kamikaze would fly directly into, unable to avoid because it was hugging the waves and had no altitude for evasive maneuvering. The loading sequence completed. The breech slammed shut with the mechanical certainty that had been drilled into the gun crew through endless exercises. The firing circuit was live. All that remained was Chief Johnson's command and Hendricks's execution. In the seconds before that command came, Hendricks thought about the strangeness of modern warfare, where victory depended on shooting at nothing, trusting in invisible radio waves and mathematical probability, rather than the direct aim and solid hits that had defined naval gunnery for centuries. The proximity fuse represented a technological leap as significant as radar or the aircraft carrier. transforming anti-aircraft defense from an art requiring exceptional skill into a science that could be systematized and taught. But understanding the technology intellectually was different from trusting it in combat. When a piloted bomb was approaching at 350 feet per second, and your life depended on a tiny radio transmitter surviving forces that would crush any normal electronic device. Hendricks had seen the training films, had heard the lectures, had been assured that proximity fuses worked. Now he would discover whether those assurances were accurate, whether engineers in laboratories thousands of miles away had truly solved problems that seemed impossible, whether mass-produced electronics could be trusted with defending his ship and his life. The kamikaze closed to 2 miles. Chief Johnson's voice came over the intercom, calm and matter-of-fact, delivering the order that would test everything: fire. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Hendricks pressed the firing key. The 5-inch .38 recoiled with familiar violence, the deck shuddering beneath his feet as the shell left the barrel at 2,800 feet per second. Through his optical sight, he watched the shell's trajectory, a barely visible trace against the grey sky, arcing downward toward the water approximately 1,000 yards ahead of the kamikaze's position. For a fraction of a second, nothing happened. Then the shell detonated 30 feet above the wavetops in a brilliant flash, exactly as Chief Johnson had predicted. The kamikaze flew directly into the expanding cloud of shrapnel. Hendricks saw pieces of the aircraft's wing separate, the engine cowling tear away, and black smoke begin streaming from the fuselage. The Zero pitched downward, no longer under control, and struck the water 500 yards from Laffey's starboard beam, disappearing in a fountain of spray and debris. The 250-kilogram bomb detonated on impact with the ocean, sending a column of water 200 feet into the air, but harming nothing except the fish. The entire engagement had lasted 11 seconds from the fire command to impact. A single shell, fired not at the target but at empty ocean, had destroyed an aircraft that should have been invulnerable to main battery fire. Chief Johnson's voice came over the intercom again, professional and calm, despite what they had just witnessed. Good shooting, resume air search, stand by for additional targets. This is what the proximity fuse had promised, and this is what it delivered: the transformation of anti-aircraft gunnery from a probability game, where dozens of shells might be required to achieve a single hit, into a precise science where one well-placed shot could guarantee a kill. The technical achievement represented by that single successful engagement was staggering. Inside the nose of the shell that had just destroyed the kamikaze was a device that had functioned flawlessly despite being subjected to forces that would destroy virtually any other electronic equipment. The moment Hendricks pressed the firing key, the shell had accelerated from 0 to 2,800 feet per second in approximately 8 milliseconds, the time required to travel the 16-foot length of the gun barrel. That acceleration translated to forces exceeding 20,000 times the force of gravity, or 20,000 Gs. A 1-ounce component inside the fuse experienced forces equivalent to weighing 1,250 pounds for those 8 milliseconds. The rugged vacuum tubes that made the proximity fuse possible had required years of development. Standard vacuum tubes manufactured for radios or other civilian applications had filaments approximately 1/1000th of an inch in diameter, suspended inside glass envelopes by delicate wire supports. These filaments would snap instantly under gun-firing forces. The proximity fuse's vacuum tubes used filaments 5 times thicker, supported at multiple points by glass beads fused directly to the filament wire. The glass envelope itself was 1/8 of an inch thick, massive compared to civilian tubes, yet still maintaining the vacuum seal necessary for electron emission. Engineers at Sylvania and RCA had tested thousands of designs before finding configurations that survived consistently. The battery providing electrical power to the fuse was equally revolutionary. Conventional batteries used liquid electrolytes that would rupture under shock, spilling corrosive chemicals that would destroy the delicate components. The proximity fuse's battery used a reserve design, where the electrolyte was stored separately from the electrodes until the moment of firing. The setback forces of gun firing drove a small plunger that punctured a seal, allowing the electrolyte to contact the electrodes and generate electrical current. This reserve battery design ensured the fuse remained inert during storage and transportation, activating only when fired, extending shelf life and improving safety. The spinning of the shell added additional complications. At 1,500 revolutions per second, centrifugal forces tried to tear components away from their mountings. Every connection, every solder joint, every mechanical assembly had to withstand not just the linear acceleration of gun firing, but also the rotational forces of sustained spinning. Engineers used special crimping techniques rather than conventional soldering for critical connections. Mechanically deforming copper sleeves around component leads to create joints that couldn't separate under stress. They potted sensitive components in special compounds that would cushion them against vibration while maintaining electrical insulation. The radio circuit's operating frequency of 180 MHz was chosen carefully. Lower frequencies would have required larger antennas that couldn't fit inside the fuse nose. Higher frequencies would have been more susceptible to atmospheric absorption and would have required even more sophisticated tube designs. 180 MHz provided the optimal balance of antenna size, atmospheric propagation, and circuit simplicity. The transmitting antenna was a simple quarter-wave stub, approximately 16 inches long, protruding from the fuse nose. The receiving antenna was a wire loop wrapped around the fuse body, electrically isolated but magnetically coupled to the transmitter. The detonation sequence occurred in microseconds. When the received signal exceeded the threshold, the thyrotron tube ionized, allowing current to flow from the battery to a small detonator assembly. This detonator contained approximately 20 grains of sensitive explosive compound that would ignite from the electrical current. The detonator's explosion initiated a booster charge of approximately 1 ounce of high explosive, which in turn initiated the main bursting charge of 4 pounds of TNT or equivalent explosive. The entire sequence, from thyrotron firing to main charge detonation, required less than 1 millisecond. By the time the pilot of the kamikaze could have seen the detonation, the shrapnel was already radiating outward at 4,000 feet per second. The effectiveness of the shrapnel pattern against aircraft had been calculated and verified through extensive testing. A 5-inch shell's casing fragmented into approximately 15,000 individual pieces upon detonation. The size distribution followed predictable patterns, with most fragments weighing less than half an ounce, but with several hundred pieces weighing between 1 and 4 ounces. Against aircraft construction of the period, which used aluminum alloys between 0.025 and 0.125 inches thick, even small fragments could penetrate. Laboratory testing demonstrated that a fragment weighing 1/4 ounce traveling at 3,000 feet per second would penetrate 0.05-inch aluminum at ranges exceeding 300 feet from the detonation point. The probability calculations for a lethal hit were straightforward once the shrapnel pattern was characterized. A Zero kamikaze presented an effective target area of approximately 400 square feet, including wings, fuselage, and control surfaces. The shrapnel pattern from a proximity-fused shell, detonating at 30 feet altitude, extended approximately 400 feet along the shell's trajectory and 200 feet perpendicular to it, covering an area of roughly 80,000 square feet. Simple geometry indicated that an aircraft flying through this pattern would encounter a fragment density of approximately 0.19 fragments per square foot, meaning the Zero's 400 square foot cross-section would likely intercept 75 or more fragments. Multiple fragments striking engines, fuel tanks, control cables, or the pilot would almost certainly result in a kill. What made the waterburst tactic particularly effective was that it removed the requirement for precise range estimation. Traditional anti-aircraft fire required calculating exactly when the shell would reach the target's altitude, setting the time fuse accordingly, and hoping the target hadn't maneuvered. Errors of even half a second would cause the shell to detonate hundreds of feet from the target, wasting the shot. But firing ahead of a low-flying kamikaze with a proximity fuse meant the shell would detonate at a predetermined location, 30 feet above the water, and the aircraft would fly into the shrapnel pattern. The gunner only needed to estimate the correct lead angle, a calculation that experienced fire controlmen could perform reliably. The tactical implications were profound. Prior to the introduction of proximity fuses and waterburst tactics, destroyers on radar picket duty had suffered grievously from low-altitude kamikaze attacks. Between January and March 1945, during operations in the Philippines, radar picket destroyers had achieved main battery hit rates against low-flying aircraft of less than 1%. Most kamikazes approaching at wavetop height reached their targets unmolested by 5-inch fire, requiring engagement by 40mm and 20mm automatic weapons that lacked the range and hitting power to guarantee kills. The result was predictable. Multiple destroyers were hit, some fatally, by aircraft that should have been within range of the most powerful anti-aircraft weapons aboard. The introduction of VT fuses and sanction of waterburst tactics changed these statistics dramatically. By April 1945, destroyers equipped with proximity fuses and trained in waterburst techniques were reporting main battery kill rates against low-flying aircraft exceeding 20% per mount. This 20-fold improvement in effectiveness meant that a kamikaze approaching at FOSTIG, wavetop height, now faced lethal fire from multiple 5-inch mounts at ranges where previously it would have been safe. The psychological impact on defending crews was equally significant, as gunners who had felt helpless against low-altitude attacks now possessed weapons that could engage effectively throughout the aircraft's approach. April 16, 1945, would prove the value of these developments under the most extreme circumstances imaginable. USS Laffey, still stationed at Radar Picket Station No. 1, endured what would become known as the most intense kamikaze attack against a single ship during the entire war. Beginning at 0830 hours and continuing for 80 minutes, Laffey's crew fought off 22 separate kamikaze attacks, including both aircraft and Bucker rocket bombs. The ship's gunners, including Fire Controlman Hendricks and Chief Johnson at Mount 52, would fire over 4,000 rounds of ammunition and employ every tactic they had learned, including repeated waterburst engagements against aircraft attempting low-altitude approaches. The attack began with 4 Aichi D-3A Val dive bombers approaching from different quadrants, coordinating their runs to divide the ship's defensive fire. Mount 52 engaged the starboard aircraft at 8,000 yards, firing proximity-fused shells in a walking barrage pattern that Chief Johnson had refined during previous engagements. The technique involved firing shells at progressively closer ranges, creating a series of shrapnel bursts that the aircraft would fly through if it maintained course. The first shell detonated 400 yards ahead of the Val. The second detonated 200 yards ahead. The third caught the aircraft directly, tearing off its left wing and sending it into the ocean 3,000 yards from the ship. But there were 3 more Vals attacking simultaneously, more than Laffey's 6 5-inch guns could engage individually. Mount 5-3 destroyed a second aircraft at 6,000 yards. Mount 5-1 damaged a third, which smoked and veered away but didn't crash. The fourth Val, coming from directly ahead where it could be engaged by only 2 mounts, pressed its attack through a curtain of 40mm and 20mm fire and struck Laffey's portside aft, penetrating the deck and exploding in the after engine room. 21 men died instantly. The ship's speed dropped to 25 knots as one engine went offline. Damage control parties immediately began containing the fires and flooding, but Laffey was wounded and the attack was just beginning. 6 minutes later, 3 Mitsubishi A6M Zeros approached at wavetop height from port, executing exactly the tactic that waterburst gunnery was designed to counter. Mount 52 trained left, depressing the barrels to -2 degrees elevation, aiming at the water 600 yards ahead of the lead aircraft. The first shot detonated, perfectly, creating a shrapnel barrier at wavetop height. The Zero flew directly into it, its engine exploding, and the aircraft cartwheeling into the ocean. The second Zero, seeing its leader destroyed, attempted to climb and circle for another approach, presenting a perfect target for Mount 5-3, which destroyed it at 4,000 yards with a conventional altitude burst. The third Zero continued its wave-top approach, either incredibly brave or unable to process what had just happened to its companions. Mount 52 fired again, the shell detonating 30 feet above the water 400 yards ahead of the aircraft. The Zero emerged from the detonation cloud damaged but still flying, trailing smoke and fuel. It managed another 300 yards before rolling inverted and striking the ocean, victim of accumulated damage from shrapnel hits that had severed control cables and punctured the fuel system. The attacks continued without pause. 2 more Vals approached from starboard. Mount 5-1 destroyed one at 7,000 yards. The second pressed through to 1,500 yards before a proximity-fused shell from Mount 52 detonated 50 feet above and behind it, shrapnel shredding the aircraft's tail surfaces and sending it into an uncontrolled spin that ended in the ocean. Chief Johnson's mount crew had now fired 17 rounds in 12 minutes, a rate of fire that was testing both the gun's mechanical systems and the crew's endurance. In the handling room below, ammunition handlers were sweating despite the ventilation, passing heavy shells from the magazine hoist to the loading tray in a rhythm that couldn't falter without reducing the mount's defensive capability. At 0900 hours, the nature of the attack changed. A Yokosuka MXY-7 Oka, called Baka or Fool by the Americans, appeared at high altitude, released from its parent bomber beyond the range of Laffey's guns. The Oka was a rocket-powered kamikaze bomb, essentially a manned missile carrying 2,600 pounds of high explosive and capable of speeds exceeding 500 miles per hour in its terminal dive. Against such targets, proximity fuses were essential because traditional time-fused shells had virtually no chance of intercepting something moving that fast through three-dimensional space. Laffey's fire control radar tracked the Oka as it began its dive from 8,000 feet. Mount 53 and Mount 52 engaged simultaneously, firing shells fused for altitude bursts along the calculated intercept trajectory. The Oka, accelerating rapidly under rocket power, required a different firing solution than conventional aircraft. The shells had to be placed where the Oka would be 3 or 4 seconds in the future, accounting for its acceleration and the shell's time of flight. Fire Controlman Hendricks had practiced these calculations during training, but theory was different from watching a rocket-powered bomb, diving toward your ship at terminal velocity. Mount 52's first shot missed ahead, the Oka's acceleration exceeding the estimated value. The second shot detonated 200 feet behind the weapon, too far for the shrapnel to be effective. The third shot, fired with adjusted lead, caught the Oka at 4,000 feet altitude. The proximity fuse sensed the target at 70 feet distance and detonated. Shrapnel struck the Oka's airframe, but the weapon was built like a bomb rather than an aircraft, with thick metal skin designed to survive penetration damage. The Oka continued its dive, trailing smoke but still under control. Mount 5-1 fired, achieving another hit at 2,000 feet that tore away part of the Oka's left wing. The weapon began rolling, losing aerodynamic stability. At 800 feet altitude, it lost control entirely and plunged into the ocean 400 yards from Laffey's bow, close enough that the explosion sent spray across the forward gun, mounts but causing no damage. The engagement demonstrated both the capabilities and limitations of proximity fuses. Against conventional aircraft with thin aluminum construction, a single proximity burst was usually lethal. Against hardened targets like the Oka, multiple hits might be required to achieve cumulative damage sufficient to destroy the weapon. This reality drove tactical doctrine that emphasized engaging hardened targets at maximum range with sustained fire, accepting that multiple shells would be required for a kill. The attack on Laffey continued for another hour. By the time the last kamikaze was destroyed or driven off at 0950 hours, the ship had been hit by 6 aircraft and 4 bombs, with over 100 men killed or wounded. But Laffey remained afloat, her damage control efforts successful despite fires, flooding, and loss of power to multiple systems. The ship's gunners had fired over 400 rounds of 5-inch ammunition, more than 70% of it proximity fused. Post-action analysis credited the ship's survival to multiple factors, but the effectiveness of VT fuses and waterburst tactics was consistently highlighted. Without proximity fuses, Laffey's 5-inch batteries would have achieved perhaps 4 or 5 kills during the engagement. With them, the confirmed count exceeded 15, with several additional probables that might have been destroyed but crashed beyond visual observation. The Japanese perspective on proximity fuses remained one of technological bewilderment throughout the war. By mid-1945, Japanese naval intelligence had accumulated reports from survivors of kamikaze attacks describing American anti-aircraft shells that seemed to explode without hitting anything, creating airbursts that destroyed aircraft through proximity alone. These reports were initially dismissed as combat confusion or exaggeration. Traditional Japanese naval doctrine emphasized direct fire and visual aiming, with anti-aircraft tactics based on massed barrage fire that created curtains of exploding shells through which enemy aircraft had to fly. The concept of shells that automatically adjusted their detonation based on proximity to the target seemed impossible to Japanese ordnance experts who understood anti-aircraft fuses as purely mechanical timing devices. Captured American proximity fuses were never recovered intact by Japanese forces. The restriction limiting their use to over-water engagements ensured that duds sank before they could be examined. Japanese technical intelligence remained ignorant of the radio principles that made VT fuses function, instead hypothesizing various mechanical or acoustic triggering mechanisms, none of which came close to the actual design. This technological blindness paralleled their earlier failures to understand Allied radar, where Japanese scientists had examined captured equipment but couldn't grasp the underlying principles or match the manufacturing precision required for key components like cavity magnetrons. The few Japanese scientists who suspected radio proximity fusing faced insurmountable obstacles in developing countermeasures or indigenous equivalents. Japan's electronics industry in 1945 was years behind American capabilities in both theoretical understanding and manufacturing infrastructure. Vacuum tube production for Japanese radios and radar sets suffered from quality control problems that resulted in failure rates exceeding 30%, unacceptable for proximity fuses where every unit had to function perfectly under extreme conditions. The precision machining required for fuse components exceeded the capabilities of most Japanese factories, which lacked the machine tools and skilled workers necessary for manufacturing to tolerances measured in thousandths of an inch. Development of Japanese proximity fuses had been attempted starting in 1943, after intelligence reports suggested Americans possessed such weapons. The research program, conducted at the Naval Technical Research Institute and several university laboratories, made minimal progress. Prototype fuses were built and tested, but none achieved reliability exceeding 50%, and most failed catastrophically under the shock of gunfiring. By 1945, with Japanese cities being devastated by B-29 raids and the home islands under blockade, the proximity fuse development program had been effectively abandoned. Engineers and scientists who might have contributed were either conscripted for more immediate military needs or simply lacked the resources to continue research. The production scale of American proximity fuse manufacturing dwarfed anything Japanese industry could have achieved even under ideal circumstances. By war's end, American factories had produced over 22 million proximity fuses of all types, including versions for 5-inch, 3-inch, and 90mm anti-aircraft shells, as well as specialized variants for rockets and mortar shells. This production volume represented an investment exceeding $1 billion, roughly equivalent to the Manhattan Project's cost, and required coordination across dozens of contractors and hundreds of subcontractors. The Eastman Kodak Company's facility in Rochester, New York, converted from producing photographic equipment to proximity fuses, eventually manufacturing over 2 million units. Workers who had been assembling cameras learned to assemble vacuum tubes and radio circuits under magnification, following procedures documented in manuals that deliberately omitted any explanation of how the devices functioned. The security classification meant that most workers never knew they were building radio transmitters, only that they were assembling precision components for anti-aircraft weapons that would protect American sailors and soldiers. The Crosley Corporation, a radio manufacturer in Cincinnati, produced similar quantities, leveraging their experience with vacuum tube manufacturing to solve quality control problems that initially plagued production. Quality control procedures were rigorous. Every proximity fuse underwent electrical testing before installation in shells. Test fixtures measured oscillator frequency, sensitivity to reflected signals, and thyrotron firing characteristics. Fuses that failed any test were disassembled, their components analyzed to identify failure modes, and the data fed back to improve manufacturing processes. This continuous quality improvement cycle ensured that reliability, initially approximately 70% in early production batches, eventually exceeded 95% by late 1944. The remaining 5% failure rate was considered acceptable, given the complexity of the device, and the reality that even a 95% effective anti-aircraft weapon was vastly superior to traditional shells with, perhaps, 5% effectiveness. The logistics of distributing 22 million proximity fuses to forces scattered across the Pacific and European theaters represented a supply chain challenge comparable to manufacturing. Special shipping containers protected fuses from rough handling during transportation aboard cargo vessels. Ammunition ships carried both conventional and proximity-fused shells in segregated magazines, ensuring that supply officers could provide appropriate mix ratios based on operational requirements. Forward area ammunition depots maintained stocks of both fuse types, allowing resupply ships to tailor their loads based on specific requests from combat units. The European theatre had received priority for proximity fuse distribution during late 1944, when German V-1 flying bombs threatened London and Allied positions in Belgium and France. Anti-aircraft batteries defending against V-1 attacks achieved kill rates exceeding 60% when equipped with proximity-fused 90mm shells, compared to approximately 24% with time-fused ammunition. This dramatic improvement validated the technology and drove increased production allocation to support both anti-aircraft defense and offensive operations as Allied forces advanced into Germany. The Pacific Theater began receiving substantial proximity fuse allocations during the Philippines campaign in late 1944 and early 1945. Initial supplies went to capital ships and cruisers, whose larger ammunition capacities allowed them to carry significant stocks of specialized ammunition. Destroyers received allocations more gradually, with priority given to radar picket destroyers that faced the most intense kamikaze attacks. By the Okinawa campaign in April and May 1945, most destroyers carried at least 50% proximity-fused ammunition for their 5-inch batteries, with some ships carrying 75% or higher for extended radar picket assignments. The tactical evolution driven by proximity fuse availability continued throughout the Okinawa campaign. Gunnery officers refined waterburst techniques, developing standardized firing solutions for various engagement geometries. Fleet training documents distributed in May 1945 included detailed procedures for engaging low-altitude targets with surface bursts, complete with tables providing aim points based on target speed, altitude, and aspect angle. These procedures transformed what had been innovative improvisation by officers like Chief Johnson into standardized doctrine that even inexperienced gunners could apply successfully. The statistical impact was measurable and significant. During the Okinawa campaign, which lasted from April through June 1945, American ships faced approximately 1,900 kamikaze attacks. Defending forces destroyed approximately 65% of attacking aircraft before they could strike targets, with 5-inch batteries equipped with proximity fuses accounting for approximately 40% of those kills. Traditional time-fused ammunition and automatic weapons accounted for the remainder. Compared to earlier campaigns where kill rates barely exceeded 30%, the improvement directly correlated with proximity, fuse deployment, and refined tactics. The cost in ships and lives was still horrific, with over 30 ships sunk and more than 300 damaged. But without proximity fuses, post-war analysis suggested losses might have been double. The kamikaze threat declined after Okinawa, not because Japanese forces abandoned the tactic, which had proven their most effective anti-ship weapon, but because they had exhausted their available aircraft and trained pilots. By July 1945, Japanese air forces retained approximately 5,000 aircraft of all types for defense of the home islands, with plans to employ them in massive kamikaze attacks against any invasion fleet. American planning for Operation Downfall, the invasion of Japan scheduled for November 1945, anticipated kamikaze attacks exceeding anything experienced at Okinawa. The invasion fleet would have carried unprecedented quantities of proximity-fused ammunition, with some estimates suggesting over 1 million rounds would have been expended in the first week of operations alone. The atomic bombings of Hiroshima and Nagasaki in August 1945 rendered these projections moot. Japan surrendered without the invasion fleet, facing the 5,000 aircraft kamikaze assault that had been anticipated. The proximity fuse's ultimate test, defending against suicidal attacks on an invasion force, never occurred. But the technology had proven itself beyond question during the campaigns it did experience, transforming anti-aircraft defense from a marginal capability into a reliable weapon that could defeat massed aerial attacks. The post-war period saw proximity fuse technology evolve rapidly as electronic miniaturization advanced. The vacuum tube circuits that had seemed impossibly small in 1945 were replaced by transistors in the 1950s, then integrated circuits in the 1960s, each generation providing greater reliability and sophistication in packages smaller than their predecessors. Modern proximity fuses, using solid-state electronics and microprocessors, bear little physical resemblance to the vacuum tube devices of World War II. Yet they operate on identical principles: emit radio waves, measure reflected signals, detonate when proximity threshold is reached. The legacy of wartime proximity fuse development extended far beyond weapons applications. The rugged electronics techniques developed for surviving gun-firing forces influenced design of equipment for aircraft, missiles, and eventually spacecraft, where similar shock and vibration resistance was required. The mass production methods developed for assembling millions of complex electronic devices containing precision components foreshadowed the consumer electronics industry that would emerge in subsequent decades. The quality control procedures and statistical process control methods employed in proximity fuse manufacturing became standard practice across electronics manufacturing worldwide. The secrecy surrounding proximity fuses remained in effect long after the war ended. Detailed technical information about circuit designs, manufacturing techniques, and performance characteristics remained classified until the 1970s, nearly 3 decades after their combat introduction. This extended classification reflected both the technology's continued military importance and the desire to prevent potential adversaries from understanding principles that might help them develop countermeasures or equivalent weapons. Even today, some aspects of modern proximity fuse design remain classified, though the basic radio reflection principle is widely understood and has been implemented by military forces worldwide. The human dimension of the proximity fuse story deserves emphasis. Fire Controlman Hendricks survived the war, rotating stateside in June 1945 after Laffey completed repairs and was deemed unfit for further combat operations due to accumulated structural damage. He had fired more than 100 rounds during various engagements, achieving personal credit for 3 confirmed aircraft destroyed and participation in collective shoots that destroyed several more. In his post-war years, Hendricks rarely spoke about his wartime experiences, a reticence common among veterans who had faced death repeatedly and lost friends to kamikaze attacks. When he did discuss the war, he emphasized not the horror or heroism, but the strange impersonal efficiency of modern warfare, where victory depended on machines and mathematics rather than courage or skill alone. Chief Gunner's Mate Johnson retired from the Navy in 1953, having served through the Korean War, where proximity fuses again proved their worth against North Korean and Chinese aircraft. In private correspondence preserved by his family, Johnson reflected on the April 16, 1945 engagement, noting that Laffey's survival had depended on every crew member performing their duties under impossible stress, but also on technological advantages that Japanese forces couldn't match. He wrote that the proximity fuse represented the culmination of American industrial and scientific superiority, but warned against over-reliance on technology at the expense of training and leadership, a balanced perspective that characterized many veterans who had experienced both the benefits and limitations of advanced weapons. The engineers and scientists who developed proximity fuses received little public recognition during their lifetimes due to classification restrictions. Merle Tuve, who directed the initial development program, continued his career in physics, eventually becoming director of the Carnegie Institution. He rarely discussed his wartime work publicly, though he acknowledged in private that the proximity fuse project had been intellectually satisfying despite its deadly purpose. The satisfaction came not from creating a better killing machine, but from solving seemingly impossible technical problems through systematic engineering, proving that disciplined scientific method could overcome obstacles that appeared insurmountable. The production workers, predominantly women who assembled proximity fuses by the thousands at Eastman, Kodak, Crosley, and other contractors, returned to civilian life with little understanding of what they had built. Security restrictions meant they never learned that the precision components they had assembled under magnification were radio transmitters that would explode shells near enemy aircraft. Many lived their entire lives without knowing the significance of their wartime work, that their careful assembly had defended ships like Laffey and saved lives of sailors like Hendricks and Johnson. This anonymous contribution, repeated across millions of individuals working in defense industries, represented the essence of total war, where victory depended not just on soldiers and sailors, but on workers whose contributions remained invisible and unrecognized. The Japanese aviators who faced proximity-fused anti-aircraft fire left few records of their experiences, as most died in their attacks. The survivors who were captured or who remained in Japan after the war occasionally mentioned in post-war interviews the uncanny accuracy of American anti-aircraft fire during the final year of the war, noting that shells seemed to explode at optimal distances regardless of evasive maneuvering. These observations, made without understanding the technology responsible, testified to the weapon's effectiveness from the victim's perspective. Several Japanese veterans specifically mentioned low-altitude attacks being countered by shells that exploded above the water ahead of their flight path, an impossibility according to their understanding of anti-aircraft gunnery, yet a reality they witnessed repeatedly before being shot down. The proximity fuse's place in military history rests not on revolutionary breakthroughs, but on systematic problem-solving applied to practical challenges. The device succeeded because engineers refused to accept that miniature radio sets couldn't survive gun-firing forces, because production workers assembled millions of units with consistent quality, because logisticians distributed them effectively across global theaters, because gunnery officers developed tactics exploiting their capabilities, and because gunners like Hendricks and Johnson trusted the technology enough to employ counterintuitive firing solutions under combat stress. Each contribution was necessary. None alone was sufficient. The combination produced a weapon system that measurably improved anti-aircraft effectiveness and saved ships and lives. The story of proximity fuses and waterburst tactics is ultimately a story about trust, the trust that engineers placed in physics and mathematics when designing devices that defied intuition, the trust that production workers placed in procedures they couldn't fully understand, the trust that gunners placed in technology that told them to shoot at nothing and expect results, and the trust that commanders placed in their crews to perform under stress that would break many people. That trust, built on demonstrated performance and refined through hard experience, transformed proximity fuses from an experimental curiosity into a combat-proven weapon that changed naval warfare. Fire Controlman Hendricks, watching the kamikaze disintegrate from his single waterburst shot on April 3, 1945, hadn't understood the engineering brilliance that made that shot possible. He didn't need to understand vacuum tube circuits or radio propagation or thyrotron switching characteristics. He only needed to trust that when Chief Johnson told him to fire into the water ahead of the target, the shell would explode at the right moment and the shrapnel would destroy the threat. That trust, earned through training and validated through success, was what allowed him to execute the seemingly impossible shot that saved his ship. The proximity fuse deserves remembrance not because it was elegant or because it represented breakthrough innovation, but because it exemplified the less glamorous but ultimately more important work of solving practical problems through systematic engineering and disciplined execution. In an era that celebrates disruption and revolutionary change, the proximity fuse reminds us that incremental improvements, when implemented systematically at scale, often prove more valuable than conceptual breakthroughs that cannot be manufactured or deployed effectively. The device succeeded because it was practical, reliable, and adequately effective, characteristics that define technology which actually matters in the real world rather than laboratories or boardrooms. The engineers who designed it, the workers who built it, the logisticians who distributed it, and the gunners who employed it all contributed essential elements to a success that belonged to no individual, but to the collective effort that characterized American industrial mobilization in World War II. That collective effort, more than any individual brilliance or heroic action, determined the outcome of the Pacific War and validated the principle that organized industrial society could produce technological advantages decisive enough to overcome tactical skill and suicidal determination. The proximity fuse, spinning at 1500 revolutions per second, while broadcasting radio waves to sense nearby objects, represented the culmination of that principle, proving that machines could perform calculations and execute actions faster and more reliably than human reflexes, transforming warfare from a contest of individual courage into a systematic application of industrial and scientific capability. For the gunners who fired proximity-fused shells into the waves ahead of attacking kamikazes, the technology didn't make combat safe or easy. It simply shifted the odds slightly in their favor, transforming an engagement where they had minimal chance of success into one where they might survive. That shift, multiplied across thousands of engagements and hundreds of ships, saved lives and ships, and ultimately contributed to victory in a war where technological superiority proved as decisive as courage or strategy. The proximity fuse's lesson, learned at terrible cost by those who died before it was perfected and deployed, remains relevant. That solving practical problems systematically and implementing solutions at scale matters more than revolutionary breakthroughs that exist only in concept. The story of why Navy gunners started shooting into waves and hit kamikazes they couldn't see is the story of technology meeting necessity, of engineering meeting combat, and of innovation meeting implementation, one spinning vacuum tube transmitter at a time. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.